In this video, I'm going to demonstrate how to carry out a binomial test using SPSS. Essentially, this type of test is utilized when you have a variable that is binary in nature. Essentially, it has two possible outcomes and they're mutually exclusive. So a classic example is flipping a coin and the outcome being either a heads or a tails. So let's say that I flip a coin 20 times. I can count up the number of heads out of those 20 coin tosses. So let's say the number of heads is my target outcome, and I count up the number of heads. It happens to be 5. So I can form a ratio out of that to the total number of coin tosses. So 5 over 20, which gives me 0.25. So that tells me the proportion of heads out of the total number of coin tosses. Now, with a binomial test, the basic idea is that when you're working with a binary variable of this nature, what you can do is you can test whether the observed proportion from your sample data is significantly different from an expected proportion. So for instance, if I was to flip a coin 20 times, I observe a sample proportion equal to 0.25, I can test whether that sample proportion is significantly different from an expected proportion, let's say 0.5, which would be expected if you have an unbiased coin. Also, the expected count for an unbiased coin, if I flip it 20 times, the expected count of heads would be 10. So what I have right here is a set of data in SPSS, and essentially in this data set I have each row represents a separate coin toss, and the outcome is reflected in this column under heads. An outcome of 1 is an indicator that the coin toss resulted in a heads. An outcome of 0 or a code of 0 indicates the observed outcome being tails. So you can see that the first outcome was heads, second one and third ones were also heads, the fourth one was tails, fifth one tails, 12th one was a heads, and so forth. So in this particular data set, it actually is set up where we have 5 heads out of 20 coin tosses. And so we can test whether or not the proportion of heads observed is significantly different from that is expected with an unbiased coin. Again, the expected probability being 0.5 for heads. So to do this, we'll go to Analyze, we'll go down to Non-Parametric Tests, and then to Legacy Dialogues. Next we'll click on Binomial, and I'm just going to reset this and show you how to do this. We'll move the heads variable over to the test variables list, and the default test proportion that you see right here is 0.5. So let me just kind of briefly take a side note here and note what I'm talking about when we're talking about the test proportion. That is the expected proportion. And what we're doing in this case right here is we're testing a hypothesis. Our null hypothesis is essentially that our observed proportion is not significantly different from 0.5, which is our expected proportion. And so if there is a difference between what we observe in our sample data and the expected proportion, we attribute that to sampling error. So we can lay out our null hypothesis in the following way. I'm going to lay this out as, with notation, as pi minus pi with a little subscript of 0 is equal to 0, meaning that there's no difference. Now, what does this mean? The pi is essentially population notation, and this first pi right here is essentially being estimated by the proportion of heads observed in my sample data. The second pi with the little subscript 0, that's the null, and that is essentially going to be our expected proportion of 0.5. So we could lay this out a little bit more clearly by just saying pi minus 0.5, which is our expected proportion, is equal to 0. So that's our null hypothesis. The alternative hypothesis, and we're going to specify essentially a non-directional hypothesis for the time being. We're going to say, we can say it's just simply pi minus 0.5 is not equal to 0. So that's essentially what we're testing. So this is essentially what we're testing with our data, whether the observed proportion from our sample data is significantly different from 0.5, which is our expected proportion. Now, it's also important to note that when you are running the binomial test in SPSS, that the test proportion that is assumed pertains to the value of the first case in your data set. So it doesn't really matter quite so much in the case where we have essentially a non-directional hypothesis and our test proportion set at 0.5. But let's say that our test proportion had been 0.7 instead. Then it will matter more because essentially what's going to happen is SPSS reads this first value and then essentially is using the test proportion of 0.7 in reference to that first value. So if I'm testing the proportion of heads, this is fine in the current in this current data set. But let's say that the first value had not been 1, but instead had been 0. And if I had set out my test proportion at 0.7, that would be incorrect because essentially then I'd be testing the proportion of tails. So it's really important that you keep in mind what your first value is in your data set and have it aligned with the proportion, your test proportion. So at any rate, let's run our analysis. So I'm going to click on OK, and we get our binomial test results. And so you can see, first of all, you see we have our variable name. It says group 1 and group 2, and then category 1 and 0. And so essentially the group 1 right here, this is associated with the category, the first value that appeared in the data set. If the first value that appeared in the data set had been 0, then this number right here would have been 0 instead of 1. And the reason why this matters is because it's this proportion right here. So we had 5 observed heads. If we divide 5 by 20, which is gets us the observed proportion, which is 0.25. And it's that proportion that is being tested against the expected proportion of 0.5. So, so again, make sure that the first observation in your data set is aligned with your target category that you're laying out for the expected proportion. So we notice then that the observed proportion is 0.25. It's definitely less than 0.5, but at this point we don't know if that difference is attributable to sampling error. So this is where we look at the p-value that is printed out, and we have an exact significance of 0.041. And so the conventional way of doing this is just to say that if your p-value is less than or equal to 0.05, which is the conventional alpha level, then we would reject the null. And so in this particular case, we would reject the null and infer that the observed proportion is significantly different from 0.5. Now, you may be asking yourself, where does this actually come from? Where does the p-value come from? So I'm going to show you really briefly a sampling distribution of proportions. And so what I've done right here is I've just created, this is a sampling distribution of proportions assuming sample sizes of 20 and assuming an expected proportion or long-range probability of heads of 0.5. So essentially, using the binomial function, we were able to actually identify, essentially we have the observed, possible outcomes of 20 coin tosses. So the K is reflecting the number of possible heads that can occur. This column right here is actually reflecting the probability of specific outcomes or specific proportions that could be observed under the null hypothesis, which is 0.5. So you can see that each set of outcomes or each value of the outcome or the frequencies are associated with a given proportion. So we had the number of heads that we observed in our data was 5. That corresponds to the 0.25 in terms of the proportion. And so you'll also notice that with 0.5 as the expected proportion, that would be this value right here. And essentially, if we just multiply that 0.5 times 20 for the coin tosses, our expected frequency is 10. So we're essentially testing the difference between these two values here to determine if the observed proportion is significantly different from that which is expected. And so looking at our sampling distribution of proportions, this is essentially, this distribution represents, if I took an infinite number of samples of size 20 and computed the proportion of heads, then they would be distributed in this kind of fashion. So it almost looks like a bell curve, and except that the bars are not actually touching. And so you can see, though, that the expected value is falling right at the center of 0.5. So the most likely or the most probable outcome, assuming that the long-range probability is 0.5 for heads, the most probable outcome for a given sample is 0.5 for the number of heads. And so we can look right here in this column right here, and this actually gives us the probability under the null of getting 10 heads, or basically 50% heads out of 20 coin tosses, which is roughly 18%. The probability of getting 5 heads, or essentially a proportion of 0.25 out of 20 coin tosses, is roughly 1.4%. Just multiply that by 100%. So you can see right here, this is what we observed in our sample data, and which is the 0.25. So that's our 0.25. This is what we're expecting, and you can see that there's a deviation between the two. And what we're trying to determine is whether or not the deviation is significant. So in other words, is the departure from the null great enough for us to reject it and infer that essentially our coin exhibited a bias? And so when we computed the p-value is actually computed by taking the probability of each of the outcomes all the way up to and including the proportion of 0.25, or essentially in terms of the frequency counts, counts of 0 all the way up to 5. So if we add all those together, we end up with this tail value right here of 0.02. So in other words, at this point and beyond, that encompasses roughly 2% of the sampling distribution of the proportions. Now, so that's actually a p-value right there, but then we also have to take into account, if we're testing a non-directional hypothesis, then we're also testing in the upper tail as well. So we're also encompassing this area as well, which essentially is incorporating outcomes of 15 through 20. So 15 through 20. So there's this p-value as well. So when we add this p-value and this p-value together, that is what produces the 0.04 that we see in our output. Now, if we were testing a directional hypothesis, for instance, let's say I was testing whether the observed proportion in my sample data is just simply significantly less than the expected proportion, then what I could do, instead of carrying out the test using a two-tail criterion, is just taking the p-value right here and splitting that in half, and that would get me a p-value that's equal to 0.02. And so going back to our sampling distribution, where we observed 5 heads for a proportion of 0.25, then we would just simply be using this value right here, which is just summing up the individual probabilities for all of these outcomes up to a count of 5, or essentially a proportion of 0.25. So that is essentially how you can carry out a binomial test where we have an expected proportion that is equal to 0.5. Now let's say instead of using 0.5, we set up our expected proportion at 0.7. So to do that, we'll go to Analyze, we'll go down to Non-Parametric Tests, Legacy Dialogues, Binomial, and we'll set this at 0.7. Okay. So in this particular case right here, we can that will be our expected proportion. We're going to compare our sample proportion against that. So I'm going to click on OK and show you what this looks like. So you can see right here that the group 1, again, it's reading that first category, and that's what we really wanted, is our target group to essentially have the value that's represented first in the data set. It makes it a lot easier for us. So you can see we have the observed and the observed proportion, and so in this particular case, it's actually kind of rounded off to a single decimal place, but if we double click on this, we still get the 0.25, and so we're still comparing the observed proportion of 0.25, but in this case we're comparing it against an expected proportion of 0.7. And you can see the exact significance here is 0.000. It's rounded off. It's actually 0.000043. And you'll notice it also says that the alternative hypothesis states that the proportion of cases in the first group is less than 0.7. So it's doing this by default. So when your proportion is not equal to 0.5, as it was in our previous examples, then the program defaults by giving you a p-value for a one-tailed test. And so it's essentially saying that because the proportion is less than, or the observed proportion is less than the expected proportion, that it's going to test whether this proportion is significantly less than this proportion. If this proportion had been greater than, then the p-value would be for a test where you're testing the greater than hypothesis. So, kind of looking back, and let's just go back here, and I'm going to set the hypothesized long-range probability, let's say, call it 0.7. And so you can see in this particular case, looking at it, that our expected proportion, our expected count of heads would be 14 in this particular case, and this is the probability distribution. So you can see in this particular case that this is the expected proportion of 0.7, and so that's that expected count of 14. So this right here is the expected proportion. And what we observed in our data, again, was we had a count of 5 for a proportion that's equal to 0.25. So essentially, this is what we observed in our data, and we're testing whether there's a significant difference between what is observed and what is expected based on our expectations of the probability being 0.7. So in this particular case, you can see that the probability value is actually rounded off pretty darn low. It's so it's actually in scientific notation. So the probability of a 5, or essentially a proportion of 0.25, is very, very low. When we add up all of the probabilities of all the events of 0 count to 5, or essentially 0 proportion up to 0.25, when we add up that area, it's actually 0.00043. And so essentially the p-value that we are reflecting right here is this right here. So it's essentially the p is equal to 0.00043. And that is what you actually observe in the SPSS output. So kind of going back right here and taking a look at it, double click on this, there's our number right there. So that's how that test was carried out. So let's now try another data set, or I've just kind of revised the data set. I've added a few more ones in there for heads. And let's keep our same proportion, our expected proportion of 0.7. So now I'm going to go to Analyze. I'm just going to reanalyze the data pretty much in the same way as before, but now I've added a few more heads in here. And when I click on OK, you can see now that our group 1, which is our heads category, we observed 10 heads, and the observed proportion was equal to 0.5, and our test proportion is equal to 0.7. So in this particular case, you can see that we're still essentially testing whether there's a significant difference between what is observed and what is expected in the data set. And you can see that our p-value is 0.048. So there still is a statistically significant difference between the observed proportion and the expected proportion. Okay, so now I'm going to try one more example where in this particular case I've got 19 heads and essentially 1 tails that's observed in the data set. And we're going to still stick with our expected proportion of 0.7. So I'm going to go to Analyze Nonparametrics again and rerun the analysis with this particular data set in mind. So I'm going to click on OK. And so now you can see that the observed frequency, or the observed count of heads, is 19, and we had one tails that was observed in the data. You'll notice again it's kind of rounded off at a single decimal place, but I'm just going to click on this and you can see the observed proportion is 0.95. So obviously the observed proportion here for tails is 0.05. So we're essentially comparing an observed proportion of 0.95 against a test proportion of 0.7, and so now you can see the exact significance at 0.008. Now notice that before, when we had our observed proportion was less than our expected proportion, it was testing in the lower tail of the sampling distribution for the proportions. In this particular case, because the observed proportion is greater than our test proportion, it's actually testing in the upper tail of the sampling distribution. So let's just take a look at our sampling distribution and see what's going on. So you can see that there's our frequency count of 19 heads. The observed proportion is 0.95. The expected proportion was 0.7, so we would have expected a frequency of 14. So you can see then that the likelihood of obtaining a count of 19 heads was if the expected proportion is 0.7, or the long-range probability of heads was 0.7, it would be about 0.68%. So in other words, it's very low probability of obtaining that particular outcome. So this is that outcome right here. And essentially, if we add the probability associated with getting a 19 to 20 right here, you can see that it encompasses 0.0076 of the sampling distribution. So in a sense, or in essence, we're taking the probabilities associated with each two outcomes and adding them. And when we do that, we end up with a combined area of 0.0076 or 0.008. So in other words, that is exactly the same area that is reflected in this tail right here, the 0.008. So that's our p-value. Okay, so showing you that, what I want to show you really quickly, I've been talking about this before, but let me just show you again. Let's say, for instance, that our first category had been, our first observation had been a tails instead of a head. So I'll just change these up. Again, there is a problem if you do not take into account or calibrate the first observation with the test proportion. So in this case, if we do this, you can see then that we have an observed proportion. The group that is coded 0, that's the observation that's now the focus, which is the tails. So in this particular case, we had one observed tails. The observed proportion is 0.1, and then your test proportion, if you were testing for heads, this is inaccurate. So make sure that you, again, that you align that first observation with the test proportion. Okay, so there is another set of options in running the binomial tests in SPSS, and here's a new data set for heads. So I've just basically kind of set this up in a new way where we have observations of 0 and 1 for heads and tails. I'll just go ahead and put that first one as a heads as well. And let's say that I want to compare against our observed proportions for heads against the expected proportions. It can be any proportion that we want. So what I'll do is I'm going to show you the second route to do this. So we're going to go to Analyze, Non-Parametric Tests, and then you can go to One Sample. And so when you go to this particular set of tests, there are various test options. We're going to leave this as a default, automatically compare observed data to hypothesized. So we're going to leave this button alone as it is, and we are going to go to click on Fields. And you can see that kind of by default it's already set up in the test fields box right here. So if you had other variables and they appear over here, just move those variables over if you're not going to be involving them in any kind of testing. So I've got heads right here, and then under Settings, you'll see you've got Choose Test, Test Options, and so forth. So under Choose Tests, I'm going to click on Customize Tests, and I'm going to click on compare observed binary probability to hypothesize. So this is the binomial test. Before I do that though, I'm also going to click on test options. And essentially I'm going to utilize, I can generate confidence intervals around the proportions observed in my data. So the default confidence interval proportion is 0.95, so I can increase or decrease this. And obviously the significance level for a 95% confidence interval would be set at 0.05. So these are defaults, and there's probably not a whole lot of need to change those unless you wanted to increase the width of your confidence intervals. So under choose test, we'll go to options here. And so now you can see that we have a box at the top. It says hypothesized proportion. So let's say I wanted to test the observed proportion of heads against a hypothesized proportion of 0.5. So essentially assuming that we have an unbiased coin. What I can do is I can click on Klopper-Pearson exact and generate a confidence interval around my observed proportion and then determine if that hypothesized proportion falls within the confidence interval or outside. So it says define success for categorical fields. So essentially, unlike the previous route, which actually relied solely on the first observation in your data set to test the observed proportion against the expected proportion or hypothesized proportion, you still have that option right here. It says use first category found in data. But if you don't want to do that, you can click on this button instead and specify what your target outcome is. So most of the time I'm kind of inclined to do that. So I'm going to click on that, and let's say that my target outcome is heads, and I'll just put a 1 in there. And then I'll hit enter, and then I can click on OK and then run, and so I get this box right here. So essentially, I want to kind of briefly note that you can get your output from this test in a couple of different ways, but essentially what you'll have is a little bit of a test of significance right here, and you'll notice that it's giving you the exact significance displayed for the test, and this is for a two-tailed test. But I'm going to click on this button right here, and this box opens up, and you can see the hypothesis summary view down here. It says view. And you can see that we can get a little bit more detail by just clicking on this button and then going down to the confidence interval summary view. So you can see that our sample estimate, the proportion of heads in our sample data was actually 0.5, which is not different from the expected proportion, and that's why the p-value that you saw in the previous table was 1. But nevertheless, if it were the case that I wanted to generate a confidence interval around my sample estimate, you'll notice that the lower bound is 0.272, the upper bound is 0.728. Okay, so there's essentially I could use a confidence interval test, or I could use the p-value that was provided under the hypothesis summary view right here, and essentially that was testing a non-directional hypothesis. If I'm using the confidence interval approach, then essentially what I could do is test determine or test my against the null hypothesis using the expected value. The expected value, or the hypothesized population value, was 0.5, and if 0.5, the expected proportion falls between the lower and the upper bound, then you would maintain the null hypothesis and conclude that we have a significant difference. Let's try another one. Let's go to, we'll rerun the analysis and use 0.7 instead. So I'm going to go back to one sample, and under options I'm going to just hypothesize proportion. I'm going to set it at 0.7. Or actually, yeah, 0.7. So we'll click on OK and click on Run. And so now you can see that we get a p-value. It's 0.048. And so what we'll do is we'll double click on this and go to our confidence interval summary view. So we saw, in this particular case, you see that our expected proportion actually falls between 0.272 and 0.278. And remember what I was showing you earlier, that the p-value that was given was for essentially a one-tailed test. That was the default in SPSS. And in fact, kind of just rerunning through the previous approach with 0.7, you'll see that we get the same value. So the 0.048, you'll notice it was for a directional hypothesis. And this is one of the differences that we get when we go through this other option right here, which is the hypothesis test summary. It's giving you a p-value for a one-sided test, but let's say that I was testing whether my sample proportion was just simply significantly different from the expected proportion of 0.7. So in other words, let's say I didn't want to actually test a directional hypothesis. Let's just say I was testing a non-directional hypothesis. Well, in that particular case, then I would not want to be relying on this p-value and this decision right here. What I would want to do is to look at using the confidence interval approach. So I can click down here, go to confidence interval summary view, and you can see that we have a lower bound of 0.272, upper bound of 0.728. The expected proportion was 0.7, which falls between those two, and so then I would actually be maintaining the null as opposed to rejecting the null. So that is one of the big differences that you have going through this alternate route right here, which is essentially if you want to test a directional hypothesis, pretty much you'll get the same results as you did before going through the previous route, going through the legacy dialogues route. Whereas if you want to test a non-directional hypothesis concerning your observed sample proportion and whether there's just simply a difference, in that particular case you would want to generate a confidence interval around that and then test whether the expected proportion or determine whether the expected proportion falls between the lower and the upper bound.